Well, hello, sixth grade science people. This is Mr. Topol coming to you virtually for today's mini lesson. I wish I could be there in person, but I'll just have to look forward to seeing you guys next week. And I hope that you enjoyed and did a wonderful job on your sixth grade toy company projects, because the idea behind that project was to look at potential energy and then kinetic energy. Today, we want to talk about kinetic energy. But first, it's been a little while since we did some math with this stuff. Not until last week, last time I saw you guys. So let's do a quick review of what we are talking about with potential energy and the math or equations that go on there. The first thing we have to look at is what factors affect each type of potential energy. We said with gravity, if it's gravitational potential, the factors that affect it are the mass. If mass goes up, energy goes up. And then another factor that affects it is the height. If something's held higher off the ground, the amount of energy will also go up. Remember that energy is the ability to cause change. So we did this a couple ways, but one of them was to drop items onto pop cans. We saw both that the higher the object was when it fell, the more change it would make as it crushed the pop can, and that the bigger the object, like that big shot put we had, the more change it would cause. The one we couldn't demonstrate, but you guys hopefully know, is gravity. And we said if gravity is higher, like if we went to a planet Jupiter, we would also get more energy. From there, we said that scientists did some work to come up with the equation that says potential energy from gravity is equal to mass times gravity times height. And we did some work with those equations. Last time that we did some math, it was on elastic potential energy, which again had some factors that went into it. We could think of stretching out a rubber band if we're talking about elastic potential energy. We know that the further we stretch it, the more energy we're going to get. So again, we'd say these are all positively related. As one goes up, so does the other. Same thing with elastic potential. The further I pull back a rubber band before I let go, the more energy is in it. The other thing that affects it is the stiffness of the rubber band. We called that the spring constant, or K. And we said the stiffer the rubber band, the more energy it takes. And we demonstrated that with some different types of really large exercise bands. I think we had Ricky up there, maybe Zachary that were up there showing off their big muscles with these exercise bands. The stiffer band was harder to move, and the further we stretched it, the more difficult it was. From there, we said scientists came up with this potential energy equation. Potential energy for elastic objects is equal to 1/2 times the spring constant, which was K, times the distance squared. Or we said we could write that as 1/2 times K times D times D. The distance is so important, it actually shows up as a factor twice. Well, what we want to talk about today is kinetic energy. So, what factors affect kinetic energy, or KE? Well, one factor that shows up is from the very definition of kinetic energy. Kinetic energy is about moving objects. So I'm going to roll something across the frame here. Oh, there it is. This rolling object has kinetic energy because it is moving. So what could I do to give it more kinetic energy? I hope somebody answered. I really can't hear you, but I'm sure at least one really bright person just yelled out, make it go faster. And that is one way to do it. So this has some kinetic energy. I can give it more kinetic energy if I make it move faster. And I can give it more if I make it move even faster. The faster something goes, the more kinetic energy it has. And that should make sense because it's changing its position. more quickly. It's causing more change. So we would say the fastness or the speed of the object is a factor in kinetic energy. If speed goes up, amount of kinetic energy goes up. But there is something else. Besides just the speed, what else do you think we could change to give something more or less kinetic energy? Again, I can't hear you guys, but I'm really hoping that somebody talked about the size, or even better, the mass. Just like mass affects potential energy, mass can also affect kinetic energy. What if I picked a really small object like this guy? Well, if this moves, that had kinetic energy because it moved. But it would have to move really fast, like really, really, really fast, to have anywhere close to the amount of kinetic energy as the much larger object that we had used before. I hope you guys appreciate the props that I pulled in random places from my house. Anyway, let's get back to kinetic energy. Speed is one factor. The other factor is the mass. If I move a very massive object, that will have more energy than a smaller object. So again, these are positively correlated. Now, we don't know if these are positively related in this type of relationship, or in this type of relationship, or in some other one, without doing some experiments. But those experiments have been well done and documented, and they tell us it's actually exactly the same relationship as this one, just with some different variables in there. So here's our equation for kinetic energy. Write this down. You absolutely want this in your notes. Even if you haven't taken any notes yet, write it down. Kinetic energy is equal to 1/2 the mass times the velocity, or the speed, squared. We are commonly going to talk about speed in things like miles per hour or kilometers per hour. But many times in science, you're going to hear people talk about the velocity. And it's useful for us to know that for right now, these are essentially the same thing. There's no real difference for this class. In 7th grade, we'll talk about the nuances and the difference. Also, if these exponents are intimidating you, you can do the same thing we did before. You can think of this as kinetic energy is equal to 1/2 mass times velocity times velocity. So there's our formula. That's how we got it. Probably not as interesting as if we did it in person. But next, let's look at some example questions. How do I apply this formula to some real things? So here's our first example question. How much kinetic energy is contained in a 6 kilogram shot put traveling at a speed of 10 meters per second? Because we're doing all of our equations in metric, these numbers might not be super familiar to you. 6 kilogram shot put is the weight of the shot put we use to crush those cans. It's 12 pounds. It's pretty hefty. And 10 meters per second is about 25 to 30 miles per hour. So not fast, but not really slow either. This should have a decent amount of energy. But let's calculate it. Step number 1 is to write the original equation as it stands. And we saw on the last piece of paper, the kinetic energy is equal to 1/2 times the mass times velocity squared. Step number 2, solve for what you need to know. Well, they're asking me how much kinetic energy. And this is already solved for kinetic energy. So I don't need to do anything special there. I'll just rewrite the equation. Kinetic energy is equal to 1/2 mass times velocity squared. Step 3, let's substitute in what we do know. Well, I don't know kinetic energy. That's why I'm doing the equation. I do know 1/2 is 1/2. Mass is in kilograms. So my mass is 6.0 kilograms. Velocity is the same idea as speed. we're told it's got a speed of 10 meters per second. So we'll plug that in. 10.0 meters per, which just means divide, second. And that gets squared. From here, we go to my calculator. And by now, you should be real familiar with how this stuff works. I brought out the big fancy calculator because that's all I have at home except for my phone, which I'm using to record. So we'll go to the big fancy calculator and we'll just type in 1/2 or 0.5 times 6 times 10, and squared means times 10 again. I hit equal and I get an answer of 300. Don't forget that you need to round, but in this case, there's no rounding necessary because there's not even decimals. And you need units. So what unit do you think this should be in? Hopefully a lot of people just shouted out that this is in joules. So the amount of kinetic energy in this shot put is 300 joules. That's actually a lot. We mentioned last week that 70 joules is enough to fracture bones. So 300 joules is a really significant amount of energy. Before we get to our last question, I've got something for you to think about for just a few seconds. Is it possible to get a softball to have this much kinetic energy? We know that when we dropped the softball on the shot put from the same height, the shot put had way more energy because it really flattened that pop can. And the softball just kind of dented it and fell off to the side. But we could get more kinetic energy out of a smaller amount of mass if we make the speed higher. So let's look at our last example problem and just see how we might go about doing that one. In this problem, I'm saying how much energy is contained in a 0.2 kilogram softball traveling at a speed of 55 meters per second. Much, much faster speed. The last one was going about 25 miles an hour. This would be going about 125 miles per hour. So, is that enough energy to match the shot put? Well, the only way for us to find out is to calculate. We already did one of these, and we've done a lot of this type, so I'm going to go through this one a little bit faster. Kinetic energy is 1/2 mass times velocity squared. We're solving for the amount of kinetic energy, so step number 2 doesn't require any change. It's still 1/2 mass times velocity squared. Step number 3 is going to substitute in what we don't know. Well, the only things that I don't know are kinetic energy, so I'll substitute in what I do know, which is the mass of 0.2 kilograms. And the velocity. This time, we see that it's traveling at 55 meters per second, very fast velocity. And I'm going to write it out twice instead of worrying about the exponent. So we'll do 55 meters per second times 55